let's get started. 3.3 times 2, second one. Again, the first derivative test. First, or I should say maybe using the first derivative test. Using the first derivative test. Because now we're going to be using it. So the first derivative test, remember what it tells us. So we have the extreme value theorem, EVT, tells us the critical values and the max and min. I should say the absolute maximum, the highest point, the lowest point, right? These are what the extreme value theorem tells us, the critical values, and the absolute max and min. The highest point to the lowest point, right? The critical values tell us these peaks and these valleys, these critical values where a change happens in the graph, right? Where a change occurs. A change from going higher to lower, right? Or lower to higher, right? These kind of peaks and valleys of the graph. The critical values tell us those spots. The first derivative test tells us when the function increases or decreases. So in the extreme value theorem, you plug into f, plug in to f of x. In the first derivative test, you plug in to f prime. Extreme value theorem and the first derivative test. First derivative test tells you what is happening with the maxes and with the increasing and decreasing. With the first derivative test, we can also tell if something is a relative max or called a local max or a local min. Can also determine a local max and local min, right? Local min. First derivative test can also determine for us whether something is a local maximum or local minimum, right? For example, if f of x changes from, right, here is where the derivative is 0. That's critical value, critical value. If the derivative changes, if f prime is positive, and then over here, f prime is negative, if we change from positive to negative, we have a local maximum. If f prime goes from positive to negative, you know you have a local maximum. Here's where f prime equals 0 again. That's one of our critical values. And if f prime goes from negative to positive, f prime goes from a negative to a positive, you know you have a local minimum. And that's what we discussed last time. We talked about the first derivative test, how you find the derivative, you find f prime, you find these critical values, and you split the graph into these kind of chunks, right? You split the graph into these chunks where you have some section, right? Some section before the critical value and some section after the critical value, right? Before the critical value, after the critical value, and you test the derivative. You test the first derivative. It's the first derivative test. Again, I feel like it's that SpongeBob meme. It's called the first derivative test, not the whatever, right? First derivative test. You plug it in the first derivative. The first chunk, plug in the derivative, see if it's positive or negative. And you only care about the signs. You only care about positive or negative. If it's positive, that means the graph is increasing. Negative, it means the graph is decreasing. And the only place the graph is going to change are these critical values. Everywhere between one critical value and the next critical value, everywhere is between those two is always going to be the same, like consistent. It's either always going to be decreasing, always increasing. It's only one type of situation. So increasing, decreasing, right? Find your derivatives. If you change from positive derivative to negative derivative, you have a local max. If you're changing from negative to positive, you have a local min. And the derivative has to be equal to 0. The derivative has to be 0. Right? 3 conditions. 0 critical value, positive to negative, 0 negative and positive. Switching signs, and a 0 derivative. So how do we then use this situation to figure out some information about a graph? Okay. So let's do an example. Let's look at an example. Use the first derivative test. Use the first derivative test to determine intervals intervals where f of x is increasing and decreasing. Use the first derivative test to determine the intervals, the sections, the chunks, right, where f prime is increasing and where f prime is decreasing. Let's find these critical values. What's a good one? That's a pretty good one here. So let's do f of x is x cubed minus 3/2 x squared. Here's a function, x cubed minus 3/2 x squared. Determine the intervals where the graph is increasing and decreasing. So the steps we take, our first step is to find the critical values. We need to determine the critical values to determine the chunks. Find our critical values to determine our chunks. So the critical values are places where the derivative equals 0 or does not exist. So to find critical values, we take the derivative, set it to 0. To find critical values, you take the derivative, set it to 0. You will be doing that a lot. In your brain, just go, got to take a derivative, set it to 0. So let's ddx this whole thing. And let's say f prime is my derivative here, use the power rule, 3x squared minus, bring the 2 down, 2 will cancel this 2 on the bottom, right? This 2, and I bring it down in front. It's going to multiply by the 3, which is going to cancel the 2. So I'm going to cancel that 2 with this 2. So it's just going to be 3 x. X to the first power, right? Because I brought the 2 down, reduced the 2 to 1. It's just a 1 now. I'll bring this 2 down. It cancels with the bottom 2 down there. If I bring this 2 down, 2 is going to cancel with the 2 down here. So I got the derivative is 3x squared minus 3. 3x squared minus 3x. Set it equal to 0. And solve for the critical values. Okay. Now how do I solve this? Okay, let's look at algebra. Solve this. I got to do some, let's see, I got a square. This is not x by itself. I got 2 x's. That means I'm probably going to have to factor. When I see this x squared, all right, all these pieces, to solve this quadratic style equation, right? It's got an exponent here. It's a polynomial equation. I have to factor into pieces. Remember my zero product property, I got to do my factoring. So I can take out a 3 and an x. So I'm going to do that. Factor out a 3 and an x. So I'm going to get 3x times x minus 1. Right? So I'm factoring, and I've got my zero product property. I've got basically 3x equals 0, so this 3x means that x is 0. And x minus 1 means that x is equal to positive 1. And these are my critical values. Anyone unsure how I got these two answers? Anybody missing this process here? Really want to see it? Let me see it. So I got 3x equals 0, which divide by 3 both sides, x is 0. And I've got x minus 1 equals 0. Right? If I divide by 3. Right? If I add 1 to both sides, that's where I got the 1. So I just, you know, when you see this, you should be able to immediately translate in your mind to these answers here. Try to see that possibility, especially this 3x. When you get a number, just a variable on the outside by itself, x is 0 is an answer, right? This x by itself means that 0 is an answer. Minus 1 means that positive 1 is an answer. So here's my critical values. Here's my critical values. So once we've found those critical values, step 2 is to create the intervals. Create the intervals. 0 and 1 are chunks, right? So I have sort of 3 sections of my graph, right? I can imagine there's 3 sections of my graph. Create a little table here. Come on now, draw a straight line. Nope. Good enough. So I have 0, I have 1, put the 0 up here. I have 0, I have 1, and I have everything to the left of 0, to the right of 1, and between 0 and 1. So these are my 3 chunks, right? I have one interval from 0, right, where x is less than 0. This chunk here, this sort of like, how do I indicate this? X less than 0. Right, I have this sort of interval here. I have where x is between 0 and 1, this chunk in here, right, between 0 to 1. And I have this chunk over here where x is greater than 1. My 3 pieces, right, my intervals of my graph. X is less than 0, right? Basically from negative infinity to 0, right? And from 1 to infinity. Negative infinity over here. You know, think about that, right? From negative infinity to 0, everything on this side, all the things on this side of the graph are always going to be it's either going to be increasing or decreasing. Everything between here and here is going to be increasing or decreasing. Like, it's one or the other. It's either going to be all increasing or all decreasing between these. And from 1 to infinity, it's either going to be always increasing or always decreasing. It's going to be one or the other. And the 0 and the 1s, this is either my max, either my graph is going to look like, it's going to look like this or like this. Right? It's going to be, at 0, it's going to be either a top peak or a bottom out like this. And the same thing at 1. It's going to be like this or like this. I don't know which one exactly. I don't know how this shape looks. I don't know yet. To figure it out, we do our first derivative test. No, maybe I'll keep those. I like those. Hold on. This is going to be here. Is it that? Or is it that? Are we at a top, a peak, or a valley? And here too, are we at a peak or a bottom? To do the test, we test our first derivative. You do the first derivative test. First derivative test. What you do is pick a number, step 3. Test a value in each interval in f prime of x. You test a value in each interval in the derivative. You pick a number in the section, any number, it does not matter, and you test to see, test each value in the interval in f prime, and you're testing, is it positive or negative? Is it positive or is it negative? Positive means you are increasing. Negative means the graph is decreasing in that interval, in that section, in that chunk. You test a chunk, test a chunk, you test a chunk, test a number in these intervals, and you see if the graph of the derivative is positive or negative. So our derivative, f prime, was 3x squared minus 3x. So we're going to pick some numbers in these intervals, and we're going to test it in this derivative. Pick some numbers in these intervals, test it in this derivative. So what's a number in the interval? What's a number less than 0? Between negative infinity to 0. Any number in this interval I can choose. I like simple numbers. I don't want to pick something complicated. Yeah, that's a beautiful number. Yeah, -1, -2, those are both great. I'm going to pick -1. Just because, right, -1 is easy to square, things like that. So then I test it in my derivative, f prime of -1. I'm going to get 3 times -1 squared minus 3 times -1. Let's see, -1 squared is +1. So this is going to be a 3 plus 3. So that's a positive number there. That means on this section, my graph is increasing. The graph of f, the graph of my original function, is increasing. Now I got to pick a number between 0 and 1. I mean, 1/2 seems the obvious choice. Then I got to test it. F prime of 1/2. Let's see, it's 3 times 1/2 squared. I'm running a space, minus 3 times 1/2. 1/2 squared is 1/4, so this is going to be 3/4 minus 3/2. 3/2 is bigger, so this is going to be negative, and this is going to be decreasing. Maybe I should do that in red. Hold on, everyone. This is going to be a negative and decreasing. right? Because 3 over 4 minus 3 over 2 is negative 3 over 2. I don't really care about the number. I just know that 3/2 is bigger than 3/4. I know this 3/2 is bigger than 3/4. So I'm taking a small number minus a big number. I know that's going to be negative. My answer is going to be a negative. Here, I mean, it didn't really matter. It was 6, right? But I just know I have a positive plus a positive. It's going to be positive. It doesn't matter what the value is. Only we care about the sign, because we only care about what? We only care about what? Increasing or decreasing. We only care about the signs. First derivative test, we only care about the signs. What do we only care about? We only care about the signs. First derivative test, do we care about the values? We don't care about the values. We only care about what? We only care about Care Bears. No, care about the signs. Yes, thank you. All right, last one. Something bigger than 1. Number greater than 1. I got to pick a number greater than 1. How about 10? Can I pick 10? Sure, why not? Doesn't matter. I could pick 1, I could pick 2, I could pick 10, I could pick 1,000. Doesn't matter. F prime of 10. 3 times 10 squared minus 3 times 10. That's going to be 10 squared is 100, 300 minus 30. That's going to be a positive number. So that's going to be another increase. So I've got my interval tests. I've tested my intervals, my chunks between the sections, right? Shows a 10 here. And this is why it does not matter what value I pick. I picked 10 because it was going to be kind of obvious. A big number minus a small number. If I picked a 2, 2 squared is 4. 4 times 3 is 12. 12, this would have been 6. 12 minus 6, right? So it still would have been positive. It does not matter which number I pick. Every single one of these is guaranteed to all be either positive or all be negative. They're all going to be the same. Guaranteed. Because the only place that it changes is at these critical values. The only place the signs change are these critical values of 0 and 1. That's where the change is going to happen. Everything over here is going to be the same, consistent in these sections. And so I got to figure out, well, what is happening in this section? That section is an increasing section. This section is a decreasing section, and that section is again an increasing section. So we only care about the signs. First derivative test, we only care about the signs. So now that we have this information about positive, negative, we can picture in our minds the shape of this graph. At the 0, let's think about this. At the 0 critical value here, is my graph, looking at the positive, looking at the change that happened here, looking at this change that happened, is my 0 spot going to be a maximum or a minimum? What's the shape of this going to be? From transitioning from this side, picture in your mind, what's the graph doing? Increasing, and then we reach something, and then we go, and we're decreasing. Graph is increasing up to this point here at 0, and then it decreases. Are we going to have a max or a min? Which one are we going to have? A max or a min? Think about the shape of the graph. If my graph is increasing on this side, increasing, and then I reach this critical value, and then I'm decreasing on this side, is it going to be like this maximum or like that minimum? People are saying maximum, maximum. Yes. Yes, it's going to be a maximum, right? We're increasing, right? The graph's going up, increasing. We reach a maximum, and then we are decreasing. So the first section is going to be like this, our maximum. Over here, second section, we are decreasing on this side. We reach a critical value, and then we are increasing on this side. So we go from decreasing to increasing. Which one are we going to be, a maximum or a minimum? Go from decreasing to increasing, decreasing to increasing. Maximum or minimum? What happened here? Maximum or minimum? What do you think? Decreasing to increasing. Is that going to be a maximum or a minimum? Anybody have an opinion? Thank you, Lizette. Yeah, minimum, right? Obviously, right? If you think about it, we're decreasing. The graph is going down. It reaches a bottom, and now we start going back up. So our graph is going to be a minimum in that spot. And so you can see in your mind, again, you can see where the shape of this graph. We're going to have increasing. It's going to reach a maximum at 0. It's going to decrease, and then it's going to reach a minimum at 1, and then increase again. This is going to be the shape of f of x. Something like this. It may go like higher and then lower, like it may look like that. It may look like this. Right? We don't really know exactly the shape of it, but we know the general idea is it curves up and down like that. Right? Here is x equals 0. Here's x equals 1, right? Our graph will look something like this, right? 0 at 0. Oopsie, God. At 0 and at 1. 2, -1, -2, right? I don't know if it's like at the top here. Maybe it peaks out down here. Maybe it looks like, goodness gracious, maybe it looks like this. Maybe it looks like this. I don't really know, but I know that there's a max at 0 and a min at 1. And so I know that about the graph based on this first derivative test. Increasing, decreasing, increasing. And so this chart here, this chart that we make, this is the answer we're looking for. This is the intervals where we are increasing, decreasing, increasing. Right? We're looking at these charts. Figuring out what the shape of this graph looks like. And there could be many shapes. Could be many shapes. Could be many different shapes. Many different shapes. But we know that there's a max at 1 and a maximum at 0 and a min at 1. Lots of different possibilities for shapes here. Let's try to clean this up a little. Sorry, everybody. I was getting too excited about math. It's a problem in my life. Good thing I became a teacher. All right. So any questions about this process that we've gone through? We found the critical values, right, our steps, found the critical values, created intervals, and then tested a value in each interval in f prime for positive, negative. Okay, we tested our intervals, found our values. Let's try another. Let's try another. Great. Yes. Wonderful. What is an ugly one? Ugly one, ugly one. Do, 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 do. Do, 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 do. Okay, that's pretty ugly. Let's try that. Another example. Find, or I should say use the first derivative, find the intervals where f is increasing or decreasing. I'm going to use the arrows because I'm lazy. Find the intervals where f of x is increasing or decreasing. So f of x is equal to this equation here. X squared minus 4 to the 2/3 power. Oof. It's a complicated equation. Find the intervals where f is increasing or decreasing. Here's this complicated equation. Follow our steps. Follow our steps. First question, find the critical values. Well, let me go back. Even before we find the critical values, let me ask you this question here. Do we need to test for continuity and differentiability? Do we need to test before we use this first derivative test, right? Do we need to check to make sure this function follows certain rules? Are there some requirements for the first derivative test? Are there some requirements where the graph is continuous and differentiable? Are there some requirements for the first derivative test? Have we stated previously, for the first derivative test that we need to have them be continuous or differentiable? In the extreme value theorem, we found the max and mins. In the first derivative test, tells us the function increase and decrease. This is why I asked this question, right? Do we need to test? Lizette Garcia, tell us, state that answer publicly, because you are correct. Garcia, tell everyone what you just said. Maybe is not a good answer, Party. So Lizette got it. Yes, that is correct. We do not care about continuity or differentiability for the first derivative test. We do not care. The only ones we care about, that's why I asked this question, the only times we care are the value theorems. Extreme value theorem, mean value theorem, intermediate value theorem, all the value theorems, those are the ones we care about, whether it's continuous or differentiable. It's got to be continuous for the intermediate and extreme. For the mean value theorem, it has to be differentiable too. Value theorems, for the first derivative test, for the second derivative test, these work on any function. The first and second derivative tests, they work everywhere. It's just the value theorems where it is restricted. Value theorems are restricted. So no, we don't care about the differentiability or continuity of the function. Oh, Jesus. We only care about it when it's an extreme value theorem. It's a value theorem. No. Only on the intermediate value theorem, the extreme value theorem, and the mean value theorem. The intermediate and extreme value theorem, all of them need to be continuous. Only the mean value theorem must be differentiable. All of them have to be continuous. Only the mean value theorem. I is intermediate. That's the one where we guarantee there's like all the points between the high and the low are touched. It touches all the points between high and low. Intermediate value theorem. Intermediate, right, between. Extreme, there's a high and a low, there's a max and a min at the critical values. Mean value theorem, that's the one about the slope. Mean value theorem is the average slope is equal to the instantaneous slope somewhere at the C value. The instantaneous slope equals the average slope somewhere. That's the mean value theorem. So only for these do we care about continuous and differentiable. We don't care about it for the first and second derivative test. So we can just do the test. We'll just do the test. The way we do the test is we find our derivative and find our critical values first. Find the critical values first. Do this derivative, set it equal to 0. So f prime is equal to, if I do ddt of this whole thing, ddx of this whole thing, do a derivative. What's my derivative going to be? Ooh. How do I do this derivative? Well, I've got a little rule here. What rule is going to apply in this situation? I got my power rule, yes. Power rule, do the power rule with the 2/3. But I have this inside part too. And that means this is a chain rule problem. Yeah, this is a chain rule problem. Exactly. So let me do the derivative of the outside. My 2/3 times x squared minus 4 to the power of, let's see, 2/3 minus 1, that's going to be negative 1/3. I'll deal with that when I clean it up later. I just want to get the derivative written down first. Bring the power, right? Bring the 2/3 down. Minus 1, negative 1/3. So that's the derivative of the outside times derivative of the inside here. X squared minus 4. Let's see. I know it's a perfect square, a difference of squares, but it doesn't really matter. I just do derivative piece by piece. Take my 2x, x squared, sorry. This becomes 2x. Derivative of 4 is 0, so it's just 2x for my derivative of the inside. Just 2x. So cleaning this up a little bit, let's see, this negative 1/3 is going to go to the denominator. 2 and 2 is going to be a 4x on the top over 3 x squared minus 4 to the 1/3 power. And I want to set this equal to 0. Set this equal to 0. And now I have to solve. Now I've got to solve this problem here. What do I do? I have this ugly fraction. This is power of 1/3. Ugly fraction with a radical denominator with a 4x on the top. How do I solve this? How do I find places where this is 0? We talked about a while ago, a couple classes ago, we talked about a simple rule, a way to think about fractions equaling 0, a way to solve them. A really easy way. Yeah, I could cross multiply. If I cross multiply, yeah, that would take the denominator out of the equation, right? If I do this denominator times a 0, this whole thing, this denominator part's just going to go away. And we can do that. Yeah, it's okay. It's okay to do that, right? We kind of have to do two things. When we're solving a fraction like this, we kind of have to do two things. Let me undo my scratch out there. We kind of have to do two parts. One, where we ignore the denominator, we use the top equal to 0. Because the only part that's going to make this equation 0 is if the top is 0, right? The only way, if you have like anything on the top, right, x over infinity, x over 9,999 equaling 0, the only way this is going to make a 0 is if the top is 0. That's the only way. The only way the problem is going to equal 0 is if the numerator is 0. So one step we take is we just use the top and make it equal 0. And we kind of like cross multiplying, right, canceling the bottom. But we cannot ignore the bottom forever. We can't just dismiss it. Oh, denominator, we care about you too. You're okay. Don't worry, we got you. We got you. What do we got to do with the denominator? How do we got to accommodate this denominator? The way we accommodate the denominator is the denominator tells us what we're not allowed to be, right? When the denominator is 0, that's where we have a does not exist, a DNE. And those are also critical values, right? Let me do this in green. Or the denominator is not allowed to be 0, right? We use the bottom, Jesus Christ, bottom is not allowed to be 0, right? Where these are the DNEs. So we kind of do two steps when we have this fraction, right? We deal with the top part, make it equal 0. We deal with the bottom part. Where would the bottom part give us problems? No, Parison, there's no x squared. We're not doing the f equation. We're doing this top equation. Oh, I see what you're saying. You already simplified. Yeah. Yeah. I see what you're saying. Yeah, exactly. The inside part, yes, this part would be 0. That's exactly correct, right? So the bottom, let's do the top part first. Of course, 4x equals 0. That just means x equals 0. That's easy, done, no problem. That's a critical value of 0. Bottom part, well, we know that 3x squared minus 4 to the 1/3 cannot be 0. So I can cancel this 3. If I cube both sides, right, to get rid of this 1/3 power, I cube both sides. Oh, and the 0 cubed is still 0. So really the only thing I care about is x squared minus 4 can't be 0, or what values I'm not allowed to be. Add 4 to both sides, add 4 to both sides, x squared equals 4. Oopsies. X squared equals 4. Oops, squared equals 4. Square root. And what are my answers? Oops. What's my answer? X equals. What's the square root of 4, everybody? Should be 2, right? Yeah, but is that the only answer? Remember, I did my square root. Back of your mind. Oh, wait, square roots. There's something about a square root. I got to remember something about a square root. Yes, thank you, and a negative square root. Plus and minus 2. So I have 2 more critical values. Very good, very good. So 0, 2, and negative 2. Those are my critical values for this part here. Okay, so let's see what we have. So we found our critical values. Let's create our chunks, plug into my first derivative, see if we can get this this equation going. So create our chart. I've got 0, put up on top, 0, negative 2, and positive 2. So here's my chunks, right? All the numbers less than negative 2, somewhere between negative 2 and 0, somewhere between 0 and 2, and somewhere between, bigger than 2. First derivative test. First derivative test. So I got to pick my numbers in my chunks, then plug them into my f prime. F prime was equal to 4x over 3x squared minus 4 to the 1/3 power. Okay, got to deal with that. That's going to be a fun equation to plug into. That's why humans invented calculators. That's why God invented calculators. So let's deal with this. And then, again, we only care positive or negative. We only care about the sign. Do we care about the value? We do not. For first derivative test, all we care about is positive or negative. So I'm going to pick a number that's less than negative 2. Somebody tell me a number. Less than negative 2. Negative 10. Wonderful. Really big number. Maybe the bigger the number will be easier to tell if it's going to be positive or negative. So let's determine this f prime of negative 10. F prime of negative 10. So I'm going to do it over here. 4 times negative 10 over 3 times negative 10 squared minus 4 to the... Okay, it's kind of an ugly number. Oh, God. Come on, computer. There we go. It's kind of an ugly number. I know that this top part is going to be negative. Right? 4 times negative 10. I know it's negative. Is the bottom part, what do you think? Is this going to be a positive number or a negative number? Let's think about this. I zoomed out already. Let's think about this up here. Is this going to be a positive or a negative down here? Negative 10 squared. So I've got negative 10 squared. Negative 10 squared, positive 10. Positive 10 minus 4, that's going to be bigger than 4, right? So that's a positive. Positive to the 1/3 is positive. Positive times positive 3. This is a positive on the bottom. So I know that negative 10 squared is positive. Bigger than 4, when I subtract them, it's still a positive. Positive to the 1/3 is a positive. Positive times a positive is a positive. So this is all positive on the bottom. Negative on the top, positive on the bottom. When I divide them, a negative divided by a positive, what do I get? I'm going to get a negative, right? So this is negative. Negative divided by a positive, my derivative of negative 10 is negative. So I have a decrease. Jeez, decrease. Oh man, we're out of time. Okay, quick. Pick a number here, I'm going to pick negative 1. Quickly determine, is f prime of negative 1 positive or negative? I've got 4 times negative 1 over negative 1 squared minus 4 to the 1/3 times 3. This top part, whoopsies. This top part is obviously a negative. Negative 1 times 4, right? Negative 1 squared is positive. Positive minus 4, that's going to be a negative. A negative to the 1/3 is negative, times this is going to be negative. So negative over a negative, this is positive. Quickly, let's determine the other ones. Here's a positive one I'm going to pick there. F prime of 1. This is 4 times 1 over 3 times 1 squared minus 4 to the 1/3. This is a positive on the top. 1 minus 4 is negative on the bottom. Positive over negative, that's negative down here. I pick, I pick a 10. F prime of 10 is going to be 4 times 10 over 10 squared. Well, 10 squared minus 4 to the 1/3 times 3. That's going to be a positive up here, positive up here. 10 squared minus 4, that's again positive there, positive, positive. So I have positive here. And so I see my charts here. I got an increasing section, a decreasing, increasing, decreasing, increasing. So I've got here I've got from decrease to increase, I have a minimum here, I have a maximum here. Gosh, computer, why are you so slow? Maximum here, got a minimum here. And that is my situation for my critical values of -2, 0, and a minimum, a maximum, and a minimum. All right, everybody. Your assignment is on Schoology. It's a handout on Kami. It's actually out of the book, if you'd like, but you can just look at that on Kami. There are 1, 2, 3, 4, 5, 6, 7, 8 equations. I want you to remember 3 to 10. 3 to 10. There are 8 equations, graphs, I should say. Equations and graphs. I want you to do what we just did with numbers 5 to 10. Look at the equations, look at the graphs, show me where intervals are, find the critical values, show me the chunks, and then use the graph to make sure you're doing it correctly as a check. You can see the graph, you can check what you did, make sure it's, find the intervals for those equations, okay? Well done today, everybody. Use this first derivative test. Check it out. Would it be helpful to have a meeting? I think we talked about tomorrow, right? Tomorrow after school? 2 to 3 o'clock? Maybe 2:15 to 3:15? Have a little session? Yes? No? Yes. Okay, great. Let's plan tomorrow, 2:15 to 3:15, study session. Study session. Goodness gracious. Session. Tomorrow, 2:15 to 3:15. All right, I'll see you all then.